Alright, hi everyone in Sydney and in Melbourne. Today I'm going to be talking about a topic which I find quite interesting, and it's computer vision. So computer vision, I think it's quite interesting for a number of reasons, and I guess the most would be the applications are so broad, right? Even things like the recent mobile phone detection cameras, right? They operate using, you might think as kind of simple applications of computer vision, right? And if we look at what's going on under the hood, it might not actually be that difficult. So what I want to go through today is a little bit about what is computer vision, and at a low level, what's happening, right? Okay. So I guess what is computer vision? Computer vision is how computers see, how they take a scene and they process what's going on. But beyond that, it's also how they understand what's going on in the scene, right? Beyond just looking and seeing like, oh, okay, this is an image. Oh, there's some guy with red hair in front of me, you know? Seeing what's actually going on. Okay. And in that, there are three main levels of computer vision. You've got low-level vision tasks, mid-level vision tasks, and high-level vision tasks. So low-level vision tasks, I like to think about as getting features from an image, right? This is things like extracting where are corners in an image, where are edges in an image, and things like that, right? Very pixel-level tasks. Then we move on to mid-level vision. So mid-level vision, we're starting to get to a little bit more structure, right? So mid-level is all about structure, and it's doing things like grouping and recognizing objects, right? We don't quite know what objects they are yet, but we know that there's something there. And then high level is understanding the semantics of the system, understanding what's actually going on, right? Seeing that, oh, there's two babies, one's wearing green, one's wearing pink, one's probably a boy, one's probably a girl, right? So let's start at a low level vision and see what happens. But first, let's look at an example of an app with computer vision. I don't know if you guys have seen the hot dog detector.
Please, God.
What will you say if I told you there is an app on the market?
Report. Just demo it.
Okay. Let's start with a hot dog.
Jin Yang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Yes, pizza.
Yeah.
Pizza.
Not hot dog?
Wait, what the fuck?
That's it? It only does hot dogs?
No, and a not hot dog.
Okay, so that was an example of a binary classification task. So something that can take an image, it can look at some features, look at some data, and see if it is a hot dog or not a hot dog, right? So that's one application. Let's go on to how something like that might work, and in general, how a computer can represent an image, right? So many of you guys probably already know, but you can represent an image as a 3D array, and you've got each pixel's X and Y coordinate as well as the RGB value at that pixel, right? And how does a computer actually do operations on these images, on pixels? We can represent a lot of transformations as matrix multiplications, right? And to do so, we often represent our pixels in homogeneous coordinates, right? So we add not only their X and Y, but we add another direction, which is sort of like a scaling, right? And we always have that coordinate as 1, right? And without going into too much on what exactly is going on here from the maths, the main idea is we can now express transformations, including translations and other rotations, dilations, all as single matrix multiplications, and we can combine them, right? So for example, we can, if we wanted to scale an object, we can represent that as multiplication by some matrix. If we wanted to translate it, we can also represent it as some matrix. And the main benefit of this in this homogeneous coordinates approach, and why I wanted to mention it, is because now we can chain many transformations just into a single total matrix, right? If we were to leave them in standard coordinates, right? Just like if I wanted to take any point in R2 or in the Cartesian plane and rotate it and translate it, I would have to have something like a matrix multiplication and add a vector. If I do this many times, you can see that we would multiply out many terms. But with this representation on how we represent images, we can do this in a single matrix multiplication. Okay, the first low-level task we're going to look at is smoothing. So if you've ever used a blur, how does your computer actually blur an image? And the idea is simple, is you take an image, or you take a pixel, and you replace it with the average weighting of the pixels around it, right? And in doing so, you're going to be losing some detail and you're going to be blurring it, right? And you're also going to be getting rid of noise, right? Any noise will be reduced, right? And how do we actually do this? We do something called applying a kernel, right? If you've ever seen a convolution before, it's called a convolution. And don't worry, I'll get into what this is. But essentially what we do is we slide over every pixel at the center and we apply some matrix. And what I mean by apply is we replace every pixel value with the average of the numbers around it. So let's see what this means, right? In this example, right, what we're doing is we want to blur our image, right? So we're using our averaging trick. And what we're going to do is we're going to find, before, these are our pixel intensities at every pixel, right? The first pixel has an intensity of 12, then the next has 28, and so forth. What do we do to blur it, right? Well, this is what we're doing to pixel value 72, right? What should this be replaced with after our blurring? Well, to apply this kernel, what it means to apply this is to replace the value that's at 72 with 1 times 35, plus 2 times 60, plus 1 times 95, plus 42 times 2, and then divide by 16. So essentially we're doing a weighted average of all the pixels around it, right? And where do we get this filter? Well, if you kind of imagine this as a 3D height map, this is just like a discretized Gaussian, or a normal distribution in 2 dimensions, right? You're putting the most weight in the middle, and then it tapers off at the edges. Okay, now that we can filter an image, and now that we can represent pixels, how do we do a basic task like detecting an edge, right? Well, okay, don't let the math scare you. What is an edge, right? An edge is simply, right, just like this black and white line here, when we go from an area that's all one color, white, to an area that's some other color, black, and then we go back to the original color, right? And if you think about the intensity, right, our intensity in our white area will be, for this example, let's say that it's 0. Then once it goes to black, it instantly shoots up to 1, right? So our intensity to the left of our edge is 0, immediately shoots up, and then to the right is 1. And what this means is we've got a massive change suddenly, right? So that kind of motivates us to think about what is the derivative at this point, right? Or how can we classify it? Well, the derivative, or simply how much it's changing, will be a lot. We're suddenly changing from no intensity to 1 intensity, right? Now, you might be thinking, like, how do we even take the derivative of this? This is clearly not continuous. We'll get to that. But what this leads us to think about is, how can we classify an edge? An edge is a maxima, or an extreme point of the derivative, and it means that the second derivative is 0, right? So the idea here is we've got a criteria for finding an maxima if we can look at the derivative. So what we do is a lot of maths on the side, but really what's going on is we make some approximation of a derivative, right, in discrete time, like over a pixel, right? And we apply it to every step, right? What is a derivative? A derivative is just talking about a change, how much something's changing. So what we do is we look at what is the pixel intensity to the right and subtract it from the pixel intensity on the left. And we use this as a simple approximation to our derivative. Now, just this simple trick allows us to do a lot. We're able to see what is our gradient at every point in an image. We're able to see in what direction is the intensity changing the most, right? And we're able to get a gradient direction. And what we often do to find edges is we smooth it out first to remove noise and then apply this derivative. And to do that, you can do that using a single matrix, right? Okay, and this brings us to how we detect edges, right? So what is happening here is we have an image of this girl, right? And what we do is we apply our derivative map. So let's blur this down a little bit just for clarity. Then we apply our derivative match. And you can see that from areas where the intensity goes from low to high, right, we get an edge, right? So this map here is just the intensity of the derivative at that point, right? Afterwards, we can do a few things to make this image a little bit, to make our edge map a little bit clearer. We can keep only the maximas, right? So we're only taking points where there's a really strong indication of an edge. The gradient is very high. And we also use a threshold. We say that okay, if our gradient changes by more than 0.7, we'll classify an edge and keep it in white, and if it's not, then we'll keep it in black, right? Okay. Quickly, I want to discuss also about how we detect corners, and I'm going to explain this intuitively, right? First, we want to think about what actually is a corner in an image, right? Well, a corner is a point where no matter what direction we move in, right, we're going to have quite a high change in our intensity, right? Similar to how we were looking at in edges, if I go in this direction, I'm going to be going from black to white. That's a drastic change in intensity. This direction, black to white. This direction, black to white. So in many directions, we've got a large change in intensity. So how might we detect a corner? Well, we can think of and we can look at what is our intensity in many directions, right? If it's large in many directions, then it's probably a corner, right? Compare this to an edge where if we go one way, if we go up and down, we're not going to change our intensity. We're going from black to black. But if we go the other way, from black to white, we're going to change our intensity a lot, right? And to do this, what we can do is we've got some way, right, to represent the change in all directions. And we look at what are called the eigenvalues, right, which you can think as the directions of maximal change. If we've got two distinct eigenvalues which are both very large, it means that in every direction we're changing very large, right? If we've got one direction where we've got a large change and the other direction has no change, we're at an edge. And if both directions have very little change, then we must be small. So the point of this area here is to think that, again, without using any like complex models or training these, simply like pixel operations, we can detect things at a low level. We can detect corners and edges, right? And now we're going to get into the main mid-level task that I want to talk about today, which is an application of computer vision, or I guess a more sort of model in computer vision, called You Only Look Once, right? And this is the key principle used in detecting objects in real time, right? If you've ever, I was talking about those mobile phone detection cameras earlier. How do they detect that something is likely to be a mobile phone? You're probably using something like this. Or if you've seen at an airport when people are walking past, sometimes they have boxes around different people, right? Or if you're an evil government surveillance agency and you want to monitor your people, you can also use this, right? And so how does this work, right? The basic idea is we want to train our model once, right? Train some machine learning model to be able to detect, is something a dog or not? Is something a hot dog or not? Is something a bicycle or not, right? And once we've got that, we want to take an image, and in a single pass of that image, without looking at it many times, right, so that it's computationally efficient, we want to determine where those objects are, right? So the algorithm kind of goes like this. We take our image, and we split it into an S by S grid of cells, right? Then for each cell, we're going to make a bunch of boxes that are centered in that cell. The one has a width of 1, one has a width of 2, one has a height of 3, right? And we make a bunch of these boxes, right? Then we use our pre-trained model to say, hey, what is the probability that this box here is a dog? What is the probability that this box here is a bicycle? And what we've now got is we've got a grid of probabilities that each box contains something, right? So we start with our S by S grid, then we make boxes in these grids, then we think about what is the probability that we have something containing a dog or a bicycle or a car in those grids. And finally, what we do is we try and figure out which boxes are the best, right? In this case, we've got many boxes that contain part of the dog, right? So we look at which box has the most overlap with other boxes, right? And there are some technical things to that implementation, but that's the main idea. And then we can output detections that there's a dog here, there's a bicycle here, and there's a car here with certain probabilities, right? So this is also, if you want to apply this or you want to use this, you don't need to like do this all from scratch, right? You can use certain libraries to do this, but it's important to know that there is an algorithm to do this, and this is how it works if you wanted to build upon it or adjust it for something else. Finally, we're going to talk about one more application, which is pretty cool, and it's one of the major applications of computer vision to estimate 3D geometry, right? So if you've ever used your phone to scan an object, right, and make a 3D model of that object, or ever taken a panorama and stitched it together, how does that work? Right? The idea here is that when we take images from different angles, we don't know what the relative change in angles of the cameras are. And we don't know the distance between the cameras. But if we could find that, if we could find what the relative change in positions and angles were, right, then we could, do some maths, put in a plane, a bit of SOHCAHTOA, some things like that, right? And we could figure out the distances between points in our image, right? So with multiple views of an object, we can recover things like distances, we can recover things like angles, all from a point. So the key problem then becomes, given a bunch of images, you don't know where they were taken, you don't know the angles they were taken, but can you kind of recover that information on what are the relative poses of the camera, right? These are called camera extrinsics. And how we do that is we take our low-level task, which was identifying corners, identifying areas which are bright, identifying edges, and we match them up with different images, right? Like on this diagram, we can see that this red point, x1, is in the center of the screen in image 1, right? It's slightly to the right in image 2, and it's more to the left in image 3, right? And you match this up, and by matching a bunch of points, you can say, hey, it's likely that image 2 was 45 degrees clockwise, more clockwise than image 1 and image 3, right? By doing so, you can recover 3D information. So one of the main innovations in this space was a paper that came out quite a while ago, in 2009, and it was called Building Rome in a Day. And what they did was they took a bunch of web-scraped images of the Colosseum, right? Then they used feature matching. They identified corners, identified bright spots that were similar in the different images, and recovered the camera poses. After that, they were able to recover the 3D information and stitch together these images to make a 3D model of the Colosseum in just a minute. And I guess another major part of this was that they did a lot of high performance computing. I guess nowadays it's your phone could do this, right? But in 2009, it's quite difficult, right? But these principles, they're exactly what are still used today, right? It's exactly the same way that your meta glasses can track an object. Your phone can measure the distance between 2 points. Essentially, you're using the same principle of recovering where the camera is relative to the object. So I hope that gives you a bit of an introduction to not only what are the applications of computer vision, but how does it actually work from a low level, right? If we were to do this all from scratch, rather than using a library, what is actually going on here? And show that the applications are quite broad.
I have a question.
Yeah.
Oh, sorry. Is this the same way AI uses to detect, not detect image, but analyze images, or is it a different method when it comes to large language model using AI? Also using pictures.
Completely different.
Yeah, I think it is completely different. I think it goes on to that last step of high-level vision. So I think some parts of this are, like the way of processing the raw data and representing the images is the same. But now when a large language model is applied to thinking about what's in the image, they are using I don't know exactly what, but they're using a lot more of that natural language processing, that a large transformer system, whereas most of the applications we looked at today were using something called CNN, so convolutional neural networks. So these were very basic, just applying a neural network to this image and going over the image. So I think perhaps it's that, but with many, many layers, as well as some other high-level things. So I don't think it's exactly the same, but I think the basic low-level stuff is the same. But when we get to that high-level understanding, it's using a lot of different things.
Thank you, Jerry.
Okay, wait. Xavier also has another question.
Yeah, I was going to ask, so with your CNN stuff, you're a lot more, I guess the things that you showed at the start was more around like object detection and classification. So that's, I guess, a bit more like standard deep learning. Do you know the reconstruction through the cameras? Did that use any deep learning, or was it mostly just around like smart maths that they were sort of doing behind the scenes? Like I guess it would have done some convolution at the start, but did it actually, was there a deep learning model behind that? Do you know? So
no, there actually wasn't a deep learning model behind that. They did that all from feature matching and extracting like geometric information. And so that was done without any deep learning there, from what I recall.
Cool.
Yeah.
Cool.
Wait, Jerry, I have another question.
Yeah.
I did send it in chat, but when you were talking about the bounding boxes, right?
Yeah.
I assume you can't make a box for every possible combination.
Yeah,
of,
that's
like,
right.
the S, right? So how do you decide like, which boxes to create?
So that is basically part of your model parameters. And you can set that up. So you can set up that I want either all the boxes, like we're making these boxes in each cell, right? And we can say that in each cell, like a simple approach would be, we'll just have these n boxes. One will be this big, one will be this big, one will be this big. But what happens is the final box that you get is an intersection of them, right? So it uses a metric called the intersection over union, where you take the intersection of those boxes, right, that are originating in your square, and you find which box maximizes the intersection of the boxes over the union. And that, in simplify, what that means is just finding the box where it has the most overlap with the other boxes, and you can crop that. So at the end, when you crop it together, if your box was too big, it'll crop down based on your intersection with the other boxes.
But I guess how come it like highlights the dog and not like a random brick on side of the road? Like how does it know to highlight a certain object?
Right. So in the you only look once, there still is a model that's pre-trained, right? So there's a model that's pre-trained on dogs, on bicycles, on cars, or whatever you're trying to find in your image, right? I'm not sure, but I think, you know, when you do CAPTCHAs and it asks, is there a dog in this image? I think that's also was to provide training image for these sort of models. But you have a model that's already trained, and that's what comes up with the probabilities of it having a dog or probability of it having a bike. It doesn't just think like, oh, there's some object here. It's thinking that there is a dog here specifically.
Thank you.
Yeah.
With the feature matching, was it all done like manually, like they had to map out the points?
No, so feature matching, I didn't get into it, but there are some algorithms to do so, basically. And essentially what you do is you find interesting features in an image, and you can find many interesting features in an image, then you compare them. So you compare that point and points around it and see if they're similar in the different images. And then you can use some statistical methods. There's an algorithm called ransack to figure out which are strongly connected. Right? Yeah. But the feature matching in itself is a whole step. Yeah.
When you triangulate with like the features with multiple cameras,
Yeah.
like is there any benefit to having more than 2 cameras?
Yeah, you get a wider, like, it depends on your application. I think the constraint is you need a minimum of three, I think, to recommend, to estimate it. And the reason being is just some like, to solve simultaneous equations with 3 unknowns, you need 3 equations, right? It's that same principle. With more than 3, I think you have a higher chance of matching those features, right? And getting more features to match. So I think it would be better.
Yeah.
Yeah.
We got 2 eyes.
Yeah.
Yeah.
Oh, true. So maybe you only need 2.
I don't know. Yeah.
You need to like, just looking at the, like, you need at least 2 to make when you've got 2 lines that are perpendicular, right? You can find the plane that goes through them, and you need that plane. It's called the epipolar plane to do that.
Motion sensors used instead of feature matching.
Motion sensor? Yeah, so in structure for motion, there's actually like a lot you can do, and especially when you're analyzing video. If you can, another task that's commonly done is, given a video, right? Given between 2 frames, how much did we move, right? If you've got a motion sensor, then even better, right? If you've got a motion sensor, then you don't need to do all that estimation. Then you can just match it up much more accurately, right? But in computer vision, you often don't have a motion sensor. So I think if you were doing a 3D scan or something, if you had a motion sensor, that would be better.
Say if I'm just measuring distance using my phone.
Oh yeah, I think what this says is you can do it without. It's probably not as good, and I think that in like the latest Apple version, I'm sure they would use some
LiDAR.
LiDAR. They use LiDAR. Okay, yeah.
Okay, for building Rome in a day,
Well, I'm assuming that you have to keep the whole object in view when you're viewing it from different angles. When they pull images from the internet, they're probably zoomed in and don't have context of the others. So how did they like connect these unrelated pictures?
Yeah, so actually you don't need the whole image in, right? Because of what we're saying is we're matching features, right? So long as you've got one point in common, right? If we look at two images and they've got the top left corner of the Colosseum, they've got that 1 pixel. If you can match that with another object from the different angle, that's exactly what you want, right? We want it so that the whole object is not in view, so then we can make our 3D model and get both sides of an object.
Okay, so it kind of figures out how to group the pictures.
Yeah,
These
and
kinds of pictures.
when I say feature match, it's not that those pixels are exactly the same and the things in a small neighborhood of those are exactly the same. It's more that it's likely that these are the same points taken from different angles. And you do that through looking at a point, looking at the places around it, and doing a transformation. So you take one image, you estimate, you find all the interesting points, right? Then you look at how those interesting points relate to each other, how those interesting points relate to each other in the other image, and then compare those relative comparisons.
From Melbourne, we've asked all the questions.
Okay, cool. Well, thank you guys so much for attending. I hope you learned something.
Thank you, Jerry.
Thank you.